All right, let's talk about spinors. I'm just going to say it up front. This is one of the most confusing, head-spinning ideas in all of physics. I mean, they're completely counterintuitive, and yet they're also one of the most fundamental things in the entire universe. They're baked into the laws of nature, and we just can't get rid of them. So what makes them so profoundly weird? Well, it boils down to this one property that just shatters our everyday intuition. The idea that you have to rotate something a full 720 degrees, that's 2 full turns, just to get it back to where it started. I mean, how is that even possible? And look, if that sounds completely nuts to you, you are not alone. This quote really hits the nail on the head. But the truly wild part isn't just that the idea exists, it's that it's mathematically sound, and as we're going to see, it's absolutely essential to how our universe is put together. So our first step is to really dig into this bizarre 720-degree property. Because if we can get our heads around this, it's the key that unlocks the entire mystery of what spinors are. But you know what? Before we can even touch spinors, we have to take a step back and look at rotation itself. It turns out the space of all possible rotations is a lot stranger than you'd think. So let's try to build a mental picture of it. Okay, so here's the main tool we're going to use. We can actually represent any rotation in 3D space with a single vector. Simple, right? The direction it points tells you the axis you're spinning around, and how long the vector is tells you the angle, how much you're spinning. And a vector with 0 length, right at the center, that just means no rotation at all. Now, this is where things get really, really weird. Imagine that this whole space of rotations is a solid ball, and the radius, the distance from the center to the edge, is 180 degrees. So if you rotate an object by 180 degrees, you've traveled from the center right to the surface of this ball. But what happens if you keep going? Well, rotating something 181 degrees is actually the exact same thing as rotating it 179 degrees in the opposite direction. What this means is that as soon as you hit that 180-degree surface, you instantly teleport to the point directly opposite you on the ball and start heading back towards the center. It's a very strange space. And this bizarre teleporting property, it has a profound consequence. It means there are fundamentally different kinds of paths you can take to get from no rotation all the way back to no rotation. The journey actually matters. And you can see the two types right here. A normal 360-degree rotation, that's a class 1 loop. You go out to the surface, you teleport once, and you come back. There's a permanent twist left in your path. You can't just smoothly shrink it back down to nothing. But a 720-degree turn, that's a class 2 loop. You go out, teleport, come back, go out again, and teleport a second time. That second teleport cancels out the first one. The whole path can now be smoothly shrunk down to a single point. The twist is gone. So what we've just uncovered is this hidden property of space itself, this weird topological twist. And to properly describe it, we're going to need a whole new kind of mathematics, something that can actually tell the difference between these two kinds of rotation. And that, right there, is what a spinor is. It's a mathematical object that actually keeps track of this hidden information. Its state doesn't just depend on its orientation, it depends on the class of rotation that got it there. So after one 360-degree rotation, a spinor's phase is flipped. It's turned negative. Only after a full 720 degrees does it get back to normal. Now, if you look at the formal maths behind this, like in textbooks on the subject, it is incredibly daunting stuff. I mean, it's really dense. But don't worry, the core idea here isn't about solving equations. It's about understanding that there's this more general, more fundamental type of transformation happening under the hood. Think of it like this, the standard 3D rotations we see every day. They're described by a set of math called SO3. But there's a deeper, more general group called SU2, and this is the math that describes spinors. And here's the key difference. The space of SU2 transformations doesn't have that weird unshrinkable twist we saw earlier. In its world, all paths can be smoothly shrunk back down to a single point. And this relationship leads to this just beautiful and powerful analogy that spinors are, in some sense, the square root of geometry. Just think about it. The square root of 4 isn't just 2. It's also -2. In the same way, for every single physical rotation we can see, there are actually 2 different mathematical representations in this deeper spinor space. This is what physicists call a double cover. For every one single rotation in our familiar world, there are 2 distinct transformations in spinor space that get you there. They give you the exact same physical result, but one is, let's say, positive and the other is negative. And that little minus sign? That's what's keeping track of whether you've done a 360-degree twist or not. It holds that memory.
Okay, so that was a lot of pretty mind-bending abstract math. And you might be sitting there thinking, why does any of this matter? What does this have to do with the real world? Well, as it turns out, it has to do with everything.
Here it is. The wave functions of all the fundamental particles that make up all the matter we see, we're talking electrons, quarks, the whole family, they aren't described by simple vectors. They are described by spinors. These fundamental building blocks of our reality intrinsically know about this bizarre 720-degree property of space. And this isn't just some quirky little detail. This spinatorial nature, that phase flip after one 360-degree turn, is directly responsible for something called the Pauli exclusion principle. That's the fundamental rule that says no two of these particles can ever be in the exact same quantum state. And without that rule, forget it. There's no chemistry, no periodic table of elements. All matter would just collapse into a boring, featureless, dense soup. I mean, just let that sink in for a second. The entire stable, complex universe that we live in, the fact that you and I even exist, is built directly on top of this completely strange, counterintuitive geometric fact that you have to rotate something twice to truly bring it back to where it started. It's incredible. But this brings us to the final, and maybe the most profound part of this whole mystery. We know spinors are real. We know they're essential. We have the math, and it works perfectly. But we're still missing the deepest why. You know, we can use the math of SU2 to predict the results of experiments with absolutely stunning accuracy. We have the how down cold. What we don't have is a deep, satisfying, intuitive gut feeling for why. Why is the universe built this way? Why is it fundamentally spinorial at its core? And hey, don't just take my word for it. As the experts in the field themselves admit, while our theories work perfectly, they don't give us a fundamental reason for why they work. It's almost impossible to really picture the deep mechanism that connects the simple act of rotating in a circle to the Pauli exclusion principle, which is the very thing that gives structure to our world. So in the end, we're left with this really tantalizing, almost philosophical question. Is our entire reality built on a deep mathematical truth that we can use with incredible precision, but that we don't yet and maybe can't ever truly understand?